Um, we looked at the asymmetry in the glaciation and deglaciation, the sawtooth pattern that we had seen over the last 400,000 years, which actually now extends to last 800,000 years. We will see that later on. Where we said during the glaciation phase the changes are slow, and then there are abrupt changes possible when the warming phase happens. How abrupt? So there is a very good example captured in the data from the North Atlantic various proxies that is now named Younger Dryas. Dryas is a flower in the Arctic that survives in the cold winter. It appeared and disappeared, leaving some evidence that the deglaciation that had started at the end of the last glacial maximum around 18,000 years ago went into an abrupt reglaciation, leaving many evidences like this. So here is the glacial polar front looking at 18,000 years ago. So this is the depth of the ocean sediment core. So you have to convert the depth into the time scale. We already saw that this was around 18,000 years ago or 20,000 years ago. The maximum polar front had come down with the land glaciers. And so you have here the glacial extent or the cold extent, the front, whatever way you want to think about it. Okay, the deepest part obviously corresponds to the oldest times going back to 18,000 years ago. As glacial melt started to happen, temperatures began to warm, so the front moved north. So the front would have moved north to, let's say, here, and then a refreezing happened, which we call the Younger Dryas, because there is another older Dryas. But the Younger Dryas around 11 to 12,000 years ago pushed the freezing back. So the front had gone up to this point and then was pushed back. So you can see that the front is here measured in polar foraminifera, which are plankton that live in the water, and they leave signatures in their shells of the temperature. Okay, that's the proxy used here. So the front had come down, which means the abundance of the polar foraminifera, forams for short, had dropped off, and then as the refreezing happened very rapidly in order of 10 to 100 years, the extent or the abundance of polar forams increased quite a bit. Where you can see this rapid change here. There's a slow deglaciation that kind of remained here. This was the older Dryas, and then the more extensive refreezing during the Younger Dryas, and then we came out of it into the beginning of the Holocene. So that evidence is also there in terms of the tree pollen found in Scotland. The cold temperatures change the vegetation types and the abundance of tree pollen. Okay, they respond to temperatures. Obviously there are details which we are not going into. So there is a late glacial refreezing during the Younger Dryas, so the temperatures were warm, let's say up to 18 degrees centigrade in England summer. They froze back down to 10 degrees. So imagine summer temperatures dropping by more than 5 degrees, down by about 8 degrees. That would have had tremendous impact on agriculture, which hadn't started in large scale yet, but it also would have affected the hunter-gatherer lifestyles as well. So there are the Younger Dryas Mountains, and then the retreat of the cold front all the way to Greenland in the post-glacial period as we warmed to the current temperatures here, or temperatures around 10,000 years ago here. Okay, other evidences showing in ice accumulation and dust measurements. Okay, so you can see the time scales here. This is a very high time resolution record from Greenland ice sheets. So you can see deglaciation. There was a jump here, slow refreezing, and then a rapid refreezing with variations of order 100 year over here, and within that you have 3 to 10 year time scales. So you can see that in the dust concentration as well. Basically, when glaciation happens, temperatures cool down, rainfall is reduced overall globally, there is more dust, and that dust accumulates in ice cores, and they are measured by the conductivity of the ice cores before bubbles are extracted and other things are measured, and so on and so forth. Okay, so there is again the theory that explains part of the at least a strong hypothesis that explains why the refreezing happened. Okay, so as the glaciers were melting, the meltwater would have filled the Great Lakes, would have run down into the Gulf of Mexico, and would have filled Labrador Sea, and there is a Lake Agassiz that actually is somewhere in this region, which had meltwater, but there was an ice bridge which was blocking its release into the Labrador Sea and Jin Sea regions. Why is that important? Now you can jump back to your knowledge of deep water formation. So if you put fresh water in this region, you're going to make it harder to form deep water by evaporation. It'll become like the North Pacific, where in the current climate the salinities are very low and it's harder to form deep waters. Okay, this should remind you also of the movie you may have seen called The Day After Tomorrow, where the temperatures being reported at the beginning of the movie are 14 degrees centigrade warmer than normal around Greenland, and before you know it, the son of the hero, who is a paleoclimate person called Dennis Quaid, I think, his son was, I forgot, what's his, yeah, anyway, doesn't matter. Okay, and his girlfriend are frozen in a library in New York City. That's kind of what happens. So if you release a lot of meltwater into this region, in the movie the Greenland glacier melts and prevents the deep water formation, but here the Laurentide ice sheet melting was dammed and suddenly released from the Hudson Bay into the regions where deep water was forming. Okay, so there is the relative CO2 increase associated with sea level rise, as you expect. Right? If the sea ice melts, you don't expect sea level to increase because that's already in the ocean. It's like an ice cube melting in your glass of cold drink. Obviously, that's not going to increase the level. But the glacier that's has frozen the water that was evaporated from the ocean and locked up on land is going to release the water, which means the sea level will rise. So you can see that the sea level rose by the amount of almost 90 meters. We went from 120 meters below the current sea level to about 30 meters below the current sea level. We're increasing sea level now by global warming and so on. The CO2 increased from less than 200 ppm to the pre-industrial level of 280, 270 ppm. Okay, so there is the change associated with the Holocene human activities and other processes. Okay, so there are consistent signatures of abrupt change in climate in the post-glacial period of the last 12,000 years, which give you a good example of what could happen in the phase that we are now in. We are releasing greenhouse gases, trapping more energy, which is leading to melting of glaciers on Greenland and parts of Antarctica. And the melting of glaciers on Greenland is accelerating because of the ice albedo feedbacks that we talked about, which means there are possibilities of abrupt melts of Greenland glaciers and Antarctic glacier, and sudden sea level increase in 10 to 100 years of many meters. Okay, lots of sea level is locked up in these glaciers.